Hi everyone, my name is Almaz Alive.
And my name is Jansir Ikram, and we are Team BTS Digital. We are the winners of the Facebook OpenEDS Sparse Semantic Segmentation Challenge. Briefly about us, we are from Kazakhstan and both of us are computer vision engineers at the BTS Digital company. So let's get started. Our presentation consists of 5 main points. First, we are going to talk about the challenge itself, about the problem state, dataset, and what metric are we going to improve. Then we will focus on our solution, baseline, and what techniques we apply to improve our score. We will finish the presentation by summarizing the main ideas and giving further thoughts on what can be done to get better results. Before going to the main part, let's watch the timeline of the competition. The competition launched on April 11th. We started competing on the 4th of July and our baseline method was ready on the 18th, so we had a bit less than 2 weeks to make a competitive solution. The main goal was to train such a model, which takes the image of an eye taken from a VR headset as an input and generates the mask by 4 classes: background, sclera, iris, and pupil. Let's deep dive into the dataset that we are provided and analyze it. The dataset was collected from 74 unique participants and contained 200 video sequences. Each sequence has approximately 150 frames, where about 7 to 14 frames are annotated and have semantic segmentation masks. In total, we have 1605 frames labeled out of about 29.5 thousand frames. Each image has size 400 to 640 pixels. Since the dataset is hand-annotated, there are always little mistakes, especially in segmentation tasks. Mostly, we faced this issue for the sclera class. For instance, this frame is missing some sclera class, which was mislabeled as background. One more example is, if to compare two neighboring frames, they are labeled differently. Taking these points into account, we conclude that mislabeling is one of the reasons why sclera was the most difficult class to obtain. Say we have ground truth mask A and predicted mask B. The score taken by the intersection area of this mask divided by their union gives us intersection over union score. The competition score was mean IOU, which is the average of IOUs of 4 aforementioned classes. So, let's jump to the solution. As stated before, the labeled images are only 5.5% of the total, so the augmentation is crucial. We used the Augmentations library to enrich our dataset. Since the sequences were captured from the static VR headset, we decided not to use aggressive augmentations. The heaviest one was the grid distortion, which narrows or widens the eye and creates a new set of unique images. For the baseline, we used unit architecture and took the SeriesNext 50 pre-trained ImageNet model as its backbone. To evaluate our model, we used a 10-fold cross-validation across video sequence. We set 8MW as the optimizer, and for the loss we took a combination of focal, dice, and binary cross-entropy losses with equal weights. Starting from 0.003, we updated the learning rate by multiplying it by 0.5 every 20 epochs and trained our network approximately for 100 epochs. At the end of the day, our local score was equal to 0.9453 and leaderboard gave us 0.9458. So our baseline is ready and the local validation correlates with leaderboard. After, we started playing around with the different backbones. As you can see from the tables, the efficient nets family was the highest scoring backbones. By the way, fold 1 was the worst, so we jumped to fold 2. As mentioned before, the sclera class is the hardest one to predict. Before 2 days to the deadline, we made a visualization of our predictions and noticed that our model mostly made mistakes on the borders. We assumed it's because of the crop augmentations, so we decided to remove them. As you can see, the score improved after removing the crop augmentations. However, we had only one submission left, so we started training fold 3 without crop and got the highest results than all models that we trained before on the local validation. Now my teammate Almaz will discuss strong techniques we used in this competition.
One technique that came in handy in this challenge was pseudo-labeling. Pseudo-labeling is applicable when there is a lot of unlabeled data, and since 95% of the dataset was not annotated, we use this approach to boost our scores. Firstly, we train our model on labeled data as usual. Once the training converges, we use the trained model to predict the sort of ground truth labels for unlabeled data, and therefore obtain pseudo-labels. After that, we use both labeled data and pseudo-labeled data to train a new model from scratch. This allows us to train on 95% previously unused data. In most of the pseudo-labeling approaches, there is a filtering step that removes bad predictions. We want to train only on our most confident predictions so that uncertain cases will not be reinforced in further training. Choosing high-quality predictions for the classification task, for example, is fairly easy since there is only one value to look at. However, the segmentation task has hundreds of thousands of these values. It's not so straightforward to filter poor samples from good ones. We've tried multiple techniques for filtering the pseudo-labels, but interestingly, using the raw pseudo-labels without any filtration worked better for us. Another thing to notice, the pseudo-labels should be obtained from an ensemble of models instead of a single model. One of the reasons is that individual models can have their own bias, and if used alone, the bias can be propagated into the dataset. Another reason is the ensembles always work better than standalone models, so you're simply getting better labels. Here are other minor details of our pseudo-label training. Firstly, we used hard labels, which is simply an argmax over the predictions. We want to try training on soft labels, which are raw softmax logits from the model, but we didn't have time for experiments. Secondly, no ensembling over different faults is allowed, since this would lead to leakage and our validation scheme would be compromised. Finally, models were trained from scratch each time, instead of fine-tuning previously trained models, to avoid bias propagation that could be introduced by those models. Here are the results of pseudo-labeling. As you can see, on average there is a 0.2% improvement compared to training only on labeled data. Another de facto standard technique always used in competitions is an ensembling. We've tried multiple ensembling techniques. So here is the raw logits output from one model. Class scores are located horizontally and the pixels are shown vertically. It is not recommended to average models' outputs on this level because each model can carry its own bias with different distribution. Usually, those outputs are run through softmax function to normalize the logits and then summed over all models and renormalized back again. Another ensembling technique is temperature shaping. It is similar to the softmax function, except the outputs are additionally taken to the power of 0.5. In a sense, such an ensembling technique enhances the distribution over classes by reducing variance. Interestingly, in our practice, the best performing ensembling technique was average across raw logits. This could be explained by the fact that we used only efficient net family of models. Some additional info about our ensembling is the following. We used flips along the x-axis. Also, we did weighted averaging so that better performing models would contribute more. And in total, our best submission consists of an ensemble of 10 models trained on 3 faults. Here are the results of our ensembling on local localization. And if you look closely, you can see that we can get a consistent gain of 0.1%. Using all of the techniques described, we were able to get the first place in the competition. However, we believe that given time, we would be able to get even better scores. Also, the code will be published at the following link. As I said earlier, we believe that there is still plenty of room for improvement. Simply training on all faults with our best pipeline could easily boost our score. Also, more rounds of pseudo-labeling could potentially increase the score too. Another thing that might be helpful is using soft labels for pseudo-labels in combination with label smoothing on ground truth data, which usually works best when annotations are noisy. Finally, a minor thing we haven't tried was fine-tuning the weights of the loss functions. This is pretty much it. We are happy to answer your questions if you have any.